Welcome class to the Math 1030 support video for handout Unit 9B on linear modeling. Okay, so we're going to take a deeper look at linear functions. And I know it's a topic that you guys have looked at for many years. It's focused a lot on junior high and high school math. But in this lesson, I'm going to focus on applying to real life, always connecting it back to a situation, a context. Okay, and that's how the book treats it as well, which I think is very beneficial because that's how you are going to usually see them in your adult life and in your jobs and things like that. So first, we think about what is a linear function. Okay? A linear function is a function that has a constant rate of change. Okay? So a function is linear if the rate of change is constant. Okay? You're always adding or subtracting the same amount as you go on in your function, as you go down your function or up your function, always the same amount. This is a contrast to exponential functions, which you are adding or subtracting off the relative amount. Okay. All right, let's take a look at two models, two places where we can apply linear functions. In section 9a, we studied tables and graphs. Below are the tables and graphs of a climbing example and a pineapple example. To B says, a group of climbers began climbing at an elevation of 6,500 feet. Okay. So this is where they began climbing, 6,500 feet. And they ascended at a steady rate of 600 vertical feet per hour. Okay, so 600 feet for 1 hour, for every hour. Into C is the next example. A small store sells fresh pineapples. Based on the data for pineapple prices, which range from $2 to $5, the store owners created a model in which a linear function is used to describe the demand, or the number of pineapples sold per day with the price. Okay? So we think about number of pineapples sold per day, this one, and the price being $2 to $5. All right, let's go ahead and continue the pattern on our table for both situations. So look at our first column here. And we have hours into the climb. So these climbers are climbing the mountain, and they're starting at 600 feet. So at 0 hours, they have 600 feet. At the first hour, they're 600 feet higher. At 0 hours, they're 6,500 feet, yeah. And at the first hour, they're 600 feet higher, so that means that they're at 7,100 feet. At the second hour, they're at 7,700 feet. Okay, so notice that each time I'm adding the same amount. Tukey goes on. So from here to here, I add 600 feet. From here to here, I add 600 feet. To get the next value, I can add a 600 more feet. And 7,700 plus 600 is 8,300. Feet. And I keep adding on 600, so we'll have 8,900 feet, and we'll have 9,500 feet, and so on. For the pineapple example, we're going to continue our table and fill in the rest of that. If the pineapple store priced their pineapples for $0, they'd be free, and they estimate that they would give away 100 pineapples that day. Now, the store would never do that because then they wouldn't make money. So that part of the model doesn't make sense, but the first part makes sense, where if they price their pineapples for $1 each, they would sell 90 of them. If they price their pineapple for $2 each, they would sell 80 of them. Okay. And so let's continue the pattern. 90 and 80. For $3, they would sell 70 pineapples that day. $4, they would sell 60 pineapples. For $5, they'd sell 50 pineapples. Okay. So each time they are subtracting off 10 pineapples. Okay, they're subtracting the same amount each time. That creates the linear graph. Okay, and so on. Okay. That's the table form, and we make a picture form. A lot of times we like pictures. Okay. So let's take a look at how that goes. They start at 6,500 feet. Let's do the climbing example here. They start at 6,500 feet, and after 1 hour, they are now 600 feet higher than that. Okay. And that one corresponds with 7,100 feet. Okay. So let's see how that goes. Okay, so let's label this axis as elevation and time. Okay, so now we know more of what's going on. Okay, let's look at our pineapple example. For every 10 pineapples, for every $1 they raise their pineapples, they will not sell as much. They'll sell 10 less that day. Okay, so we have our start. If they have no price, then they'll sell 100 pineapples. Then they'll give away 100 pineapples. Essentially, they'll sell them, quote unquote. Okay, but if you increase the price plus $1, they will sell 10 less pineapples. Okay, so our axes could be labeled price dollars, and this one on the vertical axis is going to be number of pineapples sold. Oops. Sold. Okay, got it. All right, so that's how our linear function works. Okay. Now we focus on models. Okay. The important part, one of the very important parts of a linear model is rate of change. Rate of change. So what is a rate of change? how much change is in the dependent variable is based on a change in the independent variable. Okay? So rate of change is the change between the variables because they co-vary. One changes and the other changes based off of that. So let's take a look at how much change is in the independent variable. The dependent variable, I mean. How much change is in the dependent variable is based on a change. Yeah, how much change in the independent variable? Okay, so to repeat, how much change in the independent variable is based on how much change is in the independent variable. Okay, how much change in the dependent variable is based on how much change is in the independent variable. Now there's a formula for the rate of change, and our formulas in this class, and especially in this chapter, we're going to try and use words as much as we can. Okay, so the formula is the rate of change. Okay. So the rate of change is equal to the slope, which is equal to the change in the dependent variable over the change in the independent variable. Okay, so that's what rate of change is. It's, a lot of people think of it as rise over run, and so you can think about that if you want to. But we're going to keep tying our dependent and independent variables to the situation. Okay, so we need to kind of talk in those terms. Part C says, what is the rate of change for the climbing example? The rate of change for the climbing example. Okay, change in the dependent over the independent variable. Okay, so we have to think about what the dependent variable is for the climbing example and the independent variable for the climbing example. So the change in the dependent variable is the elevation. Okay. So we're going to look at it over here. Elevation right here. This is the elevation is the dependent variable. So let's get that down a little bit. Okay. And for the climbing example, the independent variable is the time in hours. Okay, so put it over here. Okay, so I'm climbing, the change in elevation will be 600 feet for every hour. Okay, so that's how the rate of change works. So it's rate of change. How much are things changing? Okay, how much are things changing? Okay, so the change for elevation is an increase in 600 feet per 1 hour change in time. Okay. What is the rate of change for the pineapple example? Okay, so let's go over to the pineapple example. The rate of change. Again, we kind of did a little bit of analysis here that we got $1. For every $1 increase, we have 10 pineapples less, 10 pineapples less. Okay. So that's what we're going to do in our comment here. What is the rate of change for the pineapple example? Demand decreases by 10 pineapples. For every dollar, increase in price. Okay. Next question, how does the rate of change relate to the steepness or the slope of the line? Okay. So let's take a look at their slopes of these lines here. Okay, let's use this example of the climbing. How does the rate of change, how is it relate to the steepness? Okay, so for this climbing example, I'm going to make the line more steep and see what happens here. Okay, steeper line, and let's see what happens to our context. Okay, so we start at the same spot. We start at 6,500 feet. Okay, but after 1 hour, we are actually up this high. Okay, oops. After 1 hour, we're actually up this high. From 6,500 feet all the way up to 7,400 feet. Okay. So 6,500 to 7,400 is 900 feet. Okay. So as the rate of change increases, so does the steepness of the line, okay? And vice versa. So as the steepness of the line increases, the rate of change increases. Okay. Okay. So as the rate of change increases, so does the steepness of the line, and vice versa, because you can also increase the steepness of the line and then see how the rate of change increases. Okay. Let's think about changes in the dependent variable. In the climbing example, what is the change in elevation every 3 hours? Okay. So let's go back to the climbing example and take a look at the change in elevation every 3 hours. So every 3 hours, we can just pick like a spot. Let's start in maybe spot 2 here. And every 3 hours, 2 plus 3 is 5, so plus 3 hours. Now what happened to the change in the dependent variable or our elevation? Okay, so we can kind of go up to our curve here and go over to up this way until we hit the curve, and then we go to the left to see what our elevation is when we started. The elevation started at 7,700. Okay, and for 3 hours later, we can go up to the curve here, hit that, and go over this way. And we're at 9,500. Okay, so the increase in 3 hours was a gain of 95 minus 7,700. So 15 minus 7 is 8, and 8 minus 7 is 1, so 1,800 feet. Okay, so an increase of 3 hours is corresponds with a gain of 1,800 feet. So that makes sense because we're gaining 600 feet every hour. Let's go ahead and see what would happen as we put an equation to it, just to kind of use some mathematics equation, and in case things are too tedious for our graph. Okay. So the change in the dependent variable is our change in elevation for 5a. So our change in elevation is equal to 600 feet for 1 hour. Okay, and so we're going to multiply by 3 hours because that's what we are investigating what happens after 3 hours. The hours will simplify here, they'll cancel off. And we have 1,800 feet. We have our 600 times 3. Okay. Okay, so we have change in elevation. Move that down a little bit. Okay, so change in elevation. That's the rate of change. Okay, that's what they're looking for. And we're going to do our pineapple example. In the pineapple example, what is the change in demand for every increase of $3? Okay, so going into our graph, we're going to increase the price $3. Let's start at, say, $1. Okay, $1. And we're going to go over to $3, which is 1 plus $3 is $4. Okay, so my increase was, I increased the price $3. What does it do to demand? Okay, so we're going to go up from $1 to our graph, and notice that we get to 90 pineapples. And when we increase it $3, get to $4, and we go up to the line here, from $4 up to the line, and we come back over to the y-axis, or the dependent variable on the vertical axis, to see what that is. What happens when we increase the price, and it goes to 60 pineapples per day sold. Okay. So that's a decrease of 30 pineapples. So an increase of $3 corresponds to decrease of 30 pineapples. Okay. So the change in demand, change in demand for an increase of $3, every increase of $3. It could be anywhere on the graph. Okay. So our change in demand is equal to minus 10 pineapples for every dollar increase, times $3 increase. Okay, so my dollar increases will cancel, and I will get negative 30, because the 10 times 3, negative 10 times 3 is negative 30 pineapples sold per day. So it's a decrease. Okay, rate of change. Okay, rate of change in dependent variable. Okay, so this is something that companies think a lot about. So the rate of change rule is the change in the dependent variable is equal to the rate of change times the change in the independent variable. Okay, now we're going to move on to the general equation for a linear function. Okay, so we need our equation. General equation, linear function. Okay, the parts that you need of a linear function is that you need to know the dependent variable, the independent variable, the rate of change, and an initial value. So let's take a look at the form, the general formula. Again, we're going to use words on this part. So the general formula has your dependent variable out in front. And that is going to be equal to an initial value plus a rate of change times the independent variable. Okay. Now let's think about, for the climbing example, we're going to write a linear equation and we need to do it for the climbing example. So the dependent variable again was the elevation in feet. So we're going to use E for that. I'm going to symbolize that with E, the variable E. The independent variable is hours into the climb, or time. And for that variable, we're going to do T. Okay, the rate of change, again, was 600 feet per hour, right? The initial value was 6,500 feet. Initial value is what you start out with when your time is 0 or your price is 0, okay? when the dependent variable is 0, that's when your independent variable gives you the initial value. Or sorry, when the independent variable is 0, the dependent variable gives you your initial value. Okay, and so I'm going to go back to the chart here, or the graph here, to see that, to show you that. Okay, so your initial value here for climbing example is our start part, okay, right here, and it's at 6,500 feet, which is when there is 0 time, 0 hours into the climb. Okay. Okay, so the equation that we have, we're going to follow this part right here. Dependent variable, which we said was E, is equal to our initial value, which we said was 6,500 feet, plus the rate of change, which is 600 feet per hour. I'm going to kind of lose the units here for a little bit, times time, the independent variable. Okay. So just the math equation without the context is E equals 6,500 plus 600t. And we've explained our context up here. Okay, so that's good. What is the linear equation for the pineapple example? Okay, so we need our dependent variable. The dependent variable for pineapple was the demand. Okay. Or the number of pineapples. Sold per day. Okay, and we'll call that D for demand. Okay. Independent variable is the price per pineapple. Okay. Remember that the price increases and their model, so they look at the price increases. And we're going to use the little p for that. The rate of change is minus 10 pineapples sold per dollar increase. Okay. The initial value, how many they start out with. So if their price was 0, they expect to give away or sell, quote unquote, 100 pineapples. Okay. And so now we have our equation. Our dependent variable, that's the first item. So look up to B, part B, for the guidance on that. Our dependent variable was D, demand for pineapples, equal to the initial value, which was 100 pineapples per day, and the rate of change is minus 10 pineapples per dollar increase, and multiply that by the price per pineapple, P. Okay, so there's our equation. All right, as we're moving on in our exciting adventure with lines, we're going to think about the equation of a line. And this is something that you've probably learned for a lot of years. But the equation of a line, this part will be the more symbolic part. And so we will do the formula for the equation of a line in slope-intercept form. That is y equals mx plus b. Okay. Now, what does the y represent? Okay, just like our linear function equation that we've looked at so far with all of the words, y represents the dependent variable. And we usually graph that on the vertical axis. Okay, so for the climbing example, it was the elevation. For the pineapple example, it was the number of pineapples sold. But here we're going to be more generic with just variables. What does m represent? We call that the slope or the rate of change. Okay, so the increase or decrease in the dependent variable divided by the increase or decrease in the independent variable. What does x represent? The independent variable. Okay, and what does b represent? Our initial value. Okay. All right, so let's take a look at these graphs here. This is the traditional graphing that we will do. We want to graph y equals 2x plus 4 from negative 10 to 10. There's negative 10 there, 10 there. So on the homework, just go ahead and graph a couple of points and then 3 points so that you can make sure that the first two are good. And our equation is y equals 2x plus 4. So to graph these, we can just arbitrarily choose our own x's and y's. Okay. So I'm going to zoom in here a little bit. We're going to choose our own x and y, so you can pick any one you want. So I'm going to keep track here. So in class, we discussed choosing easy numbers for x's. So like 0, 1, and 2 was what they chose. So if x is 0, then I'm going to find out what my y is by substituting in the 0 for x in my equation. So like this. So y is equal to 2 times 0 plus 4. Okay. So that's 0 plus 4, which is equal to 4. So the point 0, 4 is going to be on my graph. So let's go ahead and plot that. 0 is right here. And I need 4 units up. 1, 2, 3, 4. Okay, so I just did some arbitrary units. And I'm going to put a dot at 4. My next point will be 1. X is 1. So if x is 1, y is equal to 2 times 1 plus 4, which is equal to 2 plus 4, which is equal to 6. Okay, so I'm going to draw a couple more points up here for 6. And 1 is my x, so I'm going to do plot 1, 6. Okay, let's do one more point, just make sure everything's good in the right direction. Let's do point number 2. If I say x is 2, then y is equal to 2 times 2 plus 4 is equal to 4 plus 4, which is equal to 8. Okay, so next point is 2, 8 that I'll plot. So let's put a couple more marks here. Put 8. Put the 2 over here. Okay, and there's 3 dots for our line. Okay, so there's our line, our first one. Let's go ahead and take a look at the next one. We're going to graph now 2y equals 2x plus 5. Okay, here's our x is negative 10 to 10. Okay, so we have 0 here. And we're going to draw our xy chart because we can pick up any x and you put it with the y. Okay. Let's go ahead and use our same numbers, just for simplicity's sake. 0. So if x is 0, then y is going to equal to minus 2 times 0 plus 5. That's equal to 0 plus 5, which is equal to 5. So we're going to plot 0, 5. So 0, 1, 2, 3, 4, 5. So there's 5 right here. There's 0, 5. Okay, our next point is going to be 1. When x is 1, what will we have? So y is equal to negative 2 times 1 plus 5. That's equal to negative 2 plus 5, which is equal to 3. Okay, so next we're going to plot 1, 3. So we'll do 1 here and 3 up. So that's 3 right here. All right, one more point, just to verify we're going the right direction. Point number 2. Y is equal to negative 2 times 2 plus 5. Negative 4 plus 5 equals negative 1. So we're going to plot 2, negative 1. And my 2. Oh, sorry, not negative 1, but 1. If I plotted negative 1, I'd be down here, which isn't in line with my line. So I've got to make sure that my points are good. And negative 4 plus 5 is actually positive 1. So I'm going to plot 2, 1. It's right here. Okay, so that's more in line with our points. So that should be good there. Okay. So that's what our line looks like. In number 8 here, part number 8, we're going to do a linear function from 2 data points. So we have you've heard of the old adage that 2 points determine a unique line. Well, that's true. So we're going to find 2 points, and then we can draw our line from it. What's great about this problem is that we're going to tie it to a context. Suppose your pet dog weighs 20 pounds at a year old and 34.5 pounds at 2 years old. Using these 2 data points, write a linear equation to model its growth. So his growth was 20 pounds from a year old to 34.5 pounds at 2 years old. Okay, with the power of mathematics and equations, we can look at how much the dog weighs before and after that point, or in between. Okay, so we'll show you how that is here. Set x to be the independent variable and y to be the dependent variable. Okay, so we're going to take a look at what points there are here. Our dog weighs 20 pounds. Okay, so that's at year 1. So that's important there. And there, 34.5 pounds at year 2. Okay, so those are our 2 important points. The dependent variable. Dependent variable is one that depends on another. Okay. Now our possible choices are pounds the dog weighs and years that the dog is alive. Okay. So which one depends on the other? Well, it turns out that the pounds depend on the years. Okay. So I'm going to label this here pounds is my independent variable. My dependent variable, I mean. And the years are the independent variable. Pounds depends on years. Okay, so he has different pounds as the years increase. All right, so the dependent variable is going to be the weight in pounds. The independent variable is going to be the time in years. So we're going to determine two data points. Okay, data points are of the form x comma y. Okay, where x is independent variable and y is dependent variable. Okay, so the data points will be, in this case, in our example, our x is independent, so that corresponds with years, as we can see here, and that will be the first year, and the y is my weight in pounds, so 20 pounds. So our first data point is 120, and our second one is going to be 234.5. Now, in order to build this linear function, we need to find out what the rate of change is. Okay. We know that the rate of change is the dependent variable, change in dependent variable over the change in independent variable. Okay. So for this case, we have our change in weight divided by the change in years. Okay, so we're going to define the change in weight by taking the new weight, the newest weight, subtracting off the old weight. Okay, see what that difference is. So the new weight in the second year was 34.5 pounds. Subtract off the 20 pounds it was in the first year. So 34.5 pounds in the second year, subtract 20 pounds in the first year. The change in years was the second year, first year to the second year. So we'll take our second year, subtract off our first year. And what we get is 34 minus 20 is 14.5 divided by 1. So 14.5 pounds for 1 year. Okay, so that's how much the rate is changing. So we're going to go ahead and find our initial value. Okay, so we need to find an initial value for our equation by using the formula for the equation of a line, substituting the x, y value from any point along with the slope, and solving for b. So that's the more technical part. Okay. So let's take a look at deducing the initial value by using our situation. It says that the dog weighs 20 pounds at a year old and 34.5 pounds at 2 years old. Okay. And we found the rate of change as 14.5 pounds in 1 year. Okay, so this is the first way that we're going to think about finding our initial value. Okay. So our initial value for context, by deducing it because of the context, okay? And what we want to translate our initial value to is, what does that mean for our context? It's the weight of the dog when it was born, okay? Initial value. So the weight of dog when it was born. Which means what the weight of it at year 0. Okay. Therefore, we take a value, 20 pounds at year 1, I'm going to scoot this over just a bit. I'm running out of room. And I'm going to subtract off the 14.5 pounds per year. Okay, and what do we get? We get 5.5 pounds at year 0. Okay, so that's how much the initial value is. Okay, so the second way to calculate the initial value is using y equals mx plus b, like is suggested in the problem, or the problem description here for this one right here. So we're going to put in y, which was picking a year, with 20 pounds at 1 year will work. So we pick a year. So we got 20 equals 14.5. That's the rate of change, times 1 year, plus the initial value, which is b, and I don't know the initial value, so that's why I'm solving for it. So we're saying 20 is equal to 14.5 plus b. Okay. Then we'll subtract 14.5 from both sides. Okay, this will cancel. And we'll have b is equal to 20 minus 14.5 is 5.5. Okay, so there's two ways of getting that. So the last step is to put all our values together to make the linear model. All right, so using our formula for the equation of a line, we have y is equal to the rate of change, 14.5, times x, which could be any year, plus the initial value, which is 5.5. Okay. So we put all our values together, that's what we get. So I think this model works well for times that are younger. Okay, so when the puppy or the dog was 1 year old, it weighed 20 pounds. When it was 2 years old, it weighed 34.5 pounds. And so some of the power of the mathematics, the linear equation, is that we can know the weight of the dog at, say, 1.5 years. We can use our model. Even though we don't have the data, we do have a linear model. We know that it increased steadily with a constant rate. Okay, so weight at 1.5 years means y is the weight that we want, 14.5 times 1.5 plus 5.5. Okay, and 14 times 1.5 is 21.75. We add that to 5.5. And the dog weighed 27.25 pounds at 1.5 years. Okay. We can also, that's called interpolation, where we find a point in the middle of our model. We can also extrapolate, okay, which we can use the model to predict the future. Weight at, we know that 2 years is 34.5. Let's try weight at 5 years. Okay. If the dog increases its weight at the same rate, adding on 14.5 pounds per year, we can predict the future with it, or predict how much it will weigh further down the road. So that's the power of mathematics, why we're studying these linear models. So the weight at 5 years pull it down a little bit. Corresponds with, or is equal to, y equals 14.5 times 5 plus 5.5. Okay, now 14.5 times 5 is equal to 72.5. We add 5.5 to that, we get 78. So 78 pounds is a lot of weight, but maybe that's how it works. But dogs probably don't increase their pounds, 14.5 pounds per year when they're like old, okay? So the model will break down a little bit. But for the time, for early years and early life, the model should work fine. Okay, that's all we have for linear models. Let me know if you have any questions. Hope you enjoyed the video.